Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we continue our discussion on the general rigid body kinematics. I was starting to discuss a new example. So the problem is, in the previous example we want to find the instantaneous velocity and acceleration. So that's the problem of let's say a particle with a given coordinates, fixed coordinates. So in the previous example, we want to find the instantaneous velocity, speed and acceleration of the particle, at point -3, 3, 5, right? And for this, so our solution to the problem is, in the previous example we did find that our angular velocity omega was 6i plus 3j minus 2k, and r was equal to minus 3i plus 3j plus 5k, and this was, where did we get this position vector? It is given that the particle P has a position vector minus 3, 3, 5, and then the position vector of the point B from the previous example, B was given to be minus 4i plus k. So these were the information given, and of course we want to find what is the angular velocity, we want to find the instantaneous velocity. So the instantaneous velocity is the translational velocity we want to find, which is v given by omega cross r minus b. So we plug in all these values, and we take the we take the cross product, and we find that the solution is as follows: 26j plus 15k. Okay, and then if we were to find the speed of the particle P, then it has to be the magnitude of this velocity, and we can see that this comes out to be 35, and we need to put some reference. Let's say the reference is the distance but the scales. For the distance scales we put centimeters, and for the time we put second. So the final speed is 35 centimeters per second. And then if we want to find the acceleration A of the particle is v dot, and this is also equal to omega dot cross with r minus b plus omega cross with r minus b dot, right? And we saw that b is a constant point, so the derivative of this constant point will be 0, and we see that this is omega. We also see that omega was a constant. The angular velocity of this particle was a constant, so omega dot is also 0, and so we get that this is omega cross r dot. So omega cross r dot, or omega cross v. R dot is v, and that is the acceleration. Okay, so so we will remember this result. That is, if there is a rigid body and we want to find the acceleration of any point on the rigid body, the body is rotating with some angular velocity, then the acceleration is given by the angular velocity of the body cross with the velocity of the object on the body. right? So when we talk about, so this is something we will revisit when we discuss the concept of moving frames, right? So what is the acceleration of the object of any particle in the moving frame? So we will look at this result again. So in the meantime, let us now discuss some results for general rigid body kinematics. So general rigid body kinematics. So the result says, so a body is said to be a rigid body. We have seen when the relative position between 2 points on the body is constant, right? So from the rigidity conditions, we saw that Ri minus Rj dot with Ri minus Rj is Cij square. This is a constant, and we saw that or in other words, Ri dot with Ri, these are the position vectors. So Ri dot with Ri is Di, and this is a constant. And we saw that, in other words, if we differentiate this result, we get that Ri dot with Ri Rj plus Ri dot product with Rj dot, this is 0. So Ri dot with Rj plus Ri with Rj dot, this is 0, and this is for all Ij. So this is my rigidity condition. Okay. So the general theorem, then we have some results in the form of some existence results. The first result is on the existence of the angular velocity. So let us call this result 1, the existence of the angular velocity. So let a rigid body be in a motion of with one of its particles O. Let a rigid body be in a motion with one of its particles O fixed. So we have a fixed point on the rigid body. Then there exists a unique vector. Omega, and such that the velocity of the particle P of B is given by V is omega cross R, right, where R is the position vector of the particle P relative to O, the position vector of P relative to our fixed point O, right? And in that case, so this is our velocity. Again, this is a standard result in the form of a theorem, which we will be later on using in our ideas on moving frame of reference. Then we have another result in the form of existence theorems. This is part 2. The result says, this is again on the existence of the angular velocity. So the result says, suppose the rigid body is completely in completely general motion, and let B be any be any one of its particles, right? So let B be any one of its particles, and then there exists a unique vector omega of t such that the velocity of any particle p of the body uh, is given by v, which is v translational of the fixed point b. This is my simple b here. So let me just rewrite this curly b as simple b. So that the net velocity is the translational velocity of the point b, and plus the rotational component, which is omega cross r minus b. Omega cross r minus b. So where r and b are the position vectors of the points p and b, right? So r and b are the position vectors of the points p and b. R and b are the position vectors of the point p and b, and vb is the velocity of b, and vb is the velocity of b. So that is all given. Okay, so essentially this statement says that the net motion constitutes the translational motion of a fixed point, typically the center of mass, and the rotational motion of the body around that fixed point or the axis passing through that fixed point. So then let us look at one example utilizing these results. So the example says rolling snooker ball. So this is the case of a billiard ball or a snooker ball. The problem says we have a rigid ball. Notice that we will be talking about these rigid body objects, especially the motion of these billiard balls and motion of the gyroscope, towards the very end of possibly one of the last modules, considering the complexity of motion of these objects. So we are just introducing the simplest of the motion of these objects to begin with. So the problem says a rigid ball of radius b, a rigid ball of radius b rolls without slipping on a horizontal surface. Rolls without slipping on a horizontal table. We find the most general form. Form of omega consistent with the rolling conditions. Consistent with the rolling conditions. Okay, so then so what we have is, so the problem is we have, let us try and draw the figure here. So we have a billiard ball. Let me first fix our frame of reference. So I, K, J, and the ball is rolling. Let's say it is rolling. Well, the ball is of course out of the plane, and let us say we fix the center of the ball to be C, and well, typically when we push this snooker ball, then this pushing may or may not be along the diameter of the ball. And if that is the case in general, then we don't expect the ball to be rotating about a perfectly perpendicular axis, perpendicular to the plane, right? So in general, the axis of the ball will be oblique, and we will have some sort of an angular velocity for these oblique axis, omega. Let us say this angular velocity is omega. right? And then let us say this point of this ball which is touching on the surface of the table is Q, and let us say this transverse motion of the ball is given by V of I. So this is moving forward, and so this is the setup here. The ball is rolling. The ball is rolling with velocity V of I, and unknown angular velocity omega, right? And we are going to take the center of the ball as C. We take the center of the ball C as center C of the ball as reference, and with this reference we can write down the position of any particle P on the ball. Let's say we have P which is given on the ball. So the position, so not the position but the velocity of P on the ball as V is given by V of I plus omega cross R minus C, right? So C is the position vector of point C, which is the reference point, right? And what we have is that now we can find the velocity of Q here, and in this case V of Q is the point which is touching the surface where the ball is rolling. Since the ball is rolling without slipping, we can use the rolling condition at the touching point Q. That is, the velocity at Q will be 0. So VQ is 0, but VQ using this formula is going to be V of I plus omega cross minus B of K, where B is the radius of the ball. The ball is of radius B, right? So K is the axis which is which is perpendicular to the motion of the ball. So K is this axis. Okay. So then we can find that from here we can write down what is our we can rewrite this. So VQ. So this is VQ is 0. So this is V of I plus B times K cross omega. And what we have is that we can now use so this is 0 here. We have to describe the general form of the angular velocity, right? Consistent with this rolling condition. So the general form is we are going to rewrite. So we see that what did we get? We have this relation here. So let us try to process this relation a little bit. Let us try and take a cross product of this whole relation with respect to K. So let me call this 1. So we take a cross product. We take cross product of 1 with respect to K. And we see that this is going to be V times K cross I plus B times K cross with K cross omega, right? And so what we have is that this is what we have. So now K cross I, so this is 0, and we get that this is K cross I is going to be J using our permutation, and the remaining result is that this is B times omega dot with K. So we are using the result for vector triple product. So minus k with k has to be 1 times omega, right? So this is 1. So this is going to be 0. So we see that from here we can find that omega is v of j plus this quantity which is given by omega dot with k of k, right? Well, divided by b. Okay. So here we are. This is what the problem was asking. We wanted to find the most general form of the angular velocity from the rolling condition. Notice that had we assumed that the ball was rolling along an axis perpendicular to the floor, rotating about an axis perpendicular to the floor, or about the axis which was j axis, then omega would have been simply v over j. But the fact is, this is the most general rigid body motion. There is an additional component along the k axis. So that is why our assumption of having an oblique angle of axis of rotation was a better assumption, because that's the most general form of the motion. Okay. So, or in other words, if this omega was v over b, then the motion would have been completely 2D or planar. Okay, so let me end this example, and then we have another one. Let us look at another example. The second example now is that of a wheel which is rotating about a circular motion. So wheel on a path. So the problem says we have a circular wheel of radius b, has its plane vertical, and it rolls with constant speed v. It rolls with constant speed v around a circular path, around a circular path of radius r, around a circular path of radius r on a horizontal floor. And we want to find the angular velocity of the ball. Find the angular velocity omega of the ball, of the wheel, and the acceleration of the contact particle, contact particle implying the contact point, the point where the wheel touches the floor. So the idea is we have a wheel which is rotating, which is moving along a circular path, and in doing so it is also rotating. That is how it can move ahead, right? So let us try, and we have to set up our frame of reference here. So let us say we have a frame of reference which is moving with the wheel. So what we have is, let me call this frame of reference such that the frame of reference is where I and j are the x and the y components of the frame of reference, which is along the plane of the floor, and the k axis is fixed of the moving frame. And we can see that in this moving frame, the center of the wheel is moving along the direction j hat, right? So that is fixed. It is moving along the direction j hat. The frame itself is rotating with the wheel, right? So what we have chosen is that the motion of the wheel is going to be seen with respect to the rotating frame. The rotating frame. Let's say with center O, I, J, K. The motion of the wheel is seen with respect to this rotating frame, whose x-axis is fixed with the base. Is fixed with respect to the base, the wheel base. So which means that as the wheel rotates, the frame also rotates with the wheel. Okay, so then in this, so first we have to figure out the angular velocity of the frame. The frame itself is rotating, right? So the frame angular velocity. So what is the frame angular velocity, right? And then we will, once we find this angular velocity, we can use our general result for the existence of angular velocity to find the angular velocity of the wheel in some fixed frame, right? So let us see what is the frame angular velocity. So this is going to be theta dot k hat, right? So the frame itself is rotating with the wheel, so its angular velocity is pointed in the direction of k hat, which is perpendicular to the plane of the floor, and theta dot is going to be this angle that the wheel is changing, the angular displacement of the wheel on the floor with respect to the horizontal x-axis, right? So theta dot k hat. So then the only problem now is that my I hat, the vectors I hat, are no longer constants, but they are also functions of time because they are moving with the wheel, right? So but k is constant. So k is a constant because it is always pointing in the same direction, it's not moving. Okay, so theta dot here is because the wheel is rolling. From the rolling condition, from what we see is that at the contact point we have that theta dot is v over r, right? So r is the radius. R is the radius of the wheel, right? So r is the radius of the wheel, and now so within this rotating frame, we see that the angular velocity of the wheel is, so with respect to this frame. Now in this frame the wheel is the center. So the wheel is rotating while it is moving ahead. It is rotating, and if we do a right hand rule, the direction of the motion of the wheel, the angular velocity of the motion of the wheel is going to be along the x-axis but negative to it, right? So within the rotating frame we see that the wheel angular velocity is given by omega prime, which is minus v by b times I, right? So it's minus x-axis, right? And then finally we see that the total angular velocity will be the motion of the wheel in the moving frame plus the motion of the frame itself. So we call this capital omega to be the motion of the frame angular velocity, and omega prime to be the angular velocity of the wheel in the moving frame. So we can rewrite this. This is nothing but minus v over b times I hat plus v over r times k hat. Now if we were to find the acceleration of this object, of this wheel, then notice that these quantities capital V, B and R, capital R, these are all constants of motion. These are all constant parameters. When we take a derivative of this omega with respect to time, we will see that the derivative is now going to appear in this I hat, because I hat is moving with time, because the x-axis is rotating with the wheel, and we see that di hat dt d I hat, it turns out that I hat can be viewed as r hat. So what it means is that I hat is pointing along the radial direction, and j hat is pointing along the theta direction. So we know from our standard, in the very first set of slides where we discussed the motion in Newtonian frame, in Newtonian's equations of motion, we saw that when we differentiated I with respect to time, or r hat with respect to time, dr hat dt was theta hat, and d theta hat dt was equal to minus r hat. So using all these relations, we can differentiate this relation for omega and find the acceleration, and I think that will complete the description of this wheel about this circular axis. So I stop our discussion here in this module, and in the next module we will be directly talking about the concept of rotating frames. So thank you so far for listening.